Nathan here, welcome back to another video for the video game mathematics series. And this video is not going to be strictly mathematics, it's going to cover a game algorithm that is used to determine a normal, which is a vector of length 1. So it returns a normal. How do you get a normal from a rectangular collision detection? So I'm going to draw for a bit here. Let's say we have an object, a large object here. Alright, and that object, that has a position, and we set the position to be the center point of the object. So that is the position there. This object also has a width. That's the width, and it also has a height. That is the height. Now, let's say we have a different object. Just green here. And this object, we have reached the point where we have a rectangle collision. So I'm going to draw the object here, and it's a smaller object. And it also has a position that's at the center point of the object. Right around there. This object also has a velocity, which looks like that. That's velocity. Now, we need to calculate a normal. A normal is a vector that has a length of 1. And for rectangular collision detection, a normal points in the direction where we want the object to go. If we're using vector reflection, or if we want this object to bounce, the normal points to the right. So if we want this green object to bounce off the white object, the velocity is going to point this way. So it's going to point to the right. Okay, so how do we get the normal? To get the normal, we need to get the delta, the distance, the delta, the change of position. So the big box has a position at the center point, and the green box, the smaller one, has a point at the center of it that holds a position. So we need to get the delta, which is getting a position between this point and this point. So it gets that. So that is delta. This is dx, and this is dy, and this is delta, the delta vector. So the delta vector is equal to the smaller box's position minus the bigger box's position. That gives us delta. Now we need to perform test cases. So what happens if it's on the right side? So let me choose this color. So what happens when we're on the right side? So the right side, let's look at this case. This is what's going to happen when we're on the right side, and you can visually see it. So dx, if it's on the right side, dx, as you see here, dx has to be positive, which means from here, from the smaller box to the bigger box, this is positive. If it's going to the right, it's positive change. So dx dx is positive. That's one condition. The other condition, we need to check to see if it's on the side and not the corner. We do not want, this is going to be a separate case. We do not want to have the object be on the corner if we're testing for the side. So that's going to be a completely separate case. So let me erase this. So in order to do that, we need to check to see if the absolute value of dy is less than or equal to the bigger object's height divided by 2. If it's less than or equal to that, that means it is a side collision. It can be 0, which means the actual position change will be here. So the change of y has to be less than the absolute value of the change of y. Has to be less than or equal to the height of the bigger object, the object that's going to be responsible for having the normal associated with it, the half of that height. So that is the right side. Now I also performed an additional check in the algorithm. If the x component of the velocity is negative, that means it's traveling to the left. If it's traveling to the left, we have collided on the right side. If it's traveling to the left and we've collided on the right side, which means we need to go to the right now. So the left side and top side and bottom side are pretty much the same. For the left side, we just check to see if the delta x is less than 0, which means the change is going to be on this side. It's going to the left, which means it's a negative change. Remember, the coordinate system where this is positive x, this is positive y. So this position here, that's going to be 30, 20, for example. So if something changes from here to here, that's a positive x change. If something changes from, let's say, here to here, so it's going this way, that's a negative x change. So when we test to see the left side here, we are looking at the change of x, which is negative. Top and bottom are similar. Instead of the change in x, instead of this check, we're using the change in y. And instead of the absolute value of the change of y here, we're using the absolute value of the change of x. And instead of the height here, we're checking to see the width. Let's look at a corner case. A corner case is going to be different. Let's look at the bottom right, since that's where it's closest to. So the bottom right, if the absolute value of the change of y is greater than the other object's height divided by 2. Which means the object is further down, so we're closer to the corner point here. We also need to check to see if the change of x is greater than the width of the other object divided by 2. And again, I also added the check where we see if velocity, if the x component of the velocity is negative, we are moving to the left, so it's going to be a right side collision. All right, let's take a look at another example for the corner case. We have a big object here that has a width and it has a height. And it has a center point here. We have another object. It's smaller. We're going to test to see if a collision has occurred on the top right this time. So a collision here has occurred at the top right. We know that, but how does a program know that? So let's get the delta, the change of position between object A and object B. Let's call this object A. The bigger one is object A. The smaller one is object B. So A and B. A is here and B is here. So we need to get the change from B to A. So B minus A. That will give us delta, which will be a vector. So the vector will be here. The x component will be here. The y component will be here. So the vector will look like that. So that will be D. So D is equal to B dot position minus A dot position. So B dot position minus A dot position, that will give us the delta position. Let's test top right. We know that there's a collision because we can see it. But how do we tell the program? What's the test case here? So the top right, we need to check to see if the change of x, let's set this up, top right. The top right will occur if the following is met. The change of x is greater than A dot width divided by 2. So let's visually take a look at that. The change of x is greater than A dot width divided by 2. So A dot width divided by 2, that means the change of x has to be after the length between here and here, which it is. The position is actually here. So that is correct. The change of x is here, and it is greater than A dot width divided by 2, which is the length between here and here. This is the length that is the width divided by 2. So that condition is met. We also need to check if the change of y is less than negative height divided by 2. So the change of y is less than negative a dot height divided by 2. So delta y is less than negative height divided by 2. So let's take a look at the component where it tests to see negative. Remember, if a change is upwards, XNA and Monogame use the coordinate system where to the right is positive x and to the going downwards it's positive y. So if it's changing upwards, it's going to be a negative change. If it's changing downwards, it's going to be a positive change. Okay. So that is the negative component. If it's greater than that, just like how we check to see the width divided by 2, we need to do the same thing for the height. And that is if the length is greater than the length between here and here, which it is, because that is right there. It's slightly higher. And I also added another check where the velocity of x is less than 0, which means it's traveling to the left. So those are the conditions. I explained how to find a side collision, and I showed an example of a right side. And I explained how to find a corner, and I showed the top right corner. We test all 4 sides, and then we also test the corners. And then let's just throw a simple math formula here. If it's a collision on the right, if it's a collision on the right side, the normal is going to equal 1, 0. The normal is a vector that has a length of 1. The normal is pointing to the right, so it's positive x change. This here, that's positive x change. So it's pointing to the right. Left, the normal is going to equal negative 1, 0. It's pointing to the left. Alright, let's look at the top condition here. Top, that's going to be a normal that is 0, negative 1. It points upwards, which is negative in the y direction. And then bottom, that's going to be a normal that is 0, 1. It points in the positive 1, positive y direction. So if the right condition is met, it'll return a normal that is 1, 0. If the left condition is met, it will return a normal that is negative 1, 0. If the top condition is met, it will return a normal that is 0, negative 1. If the bottom condition is met, it will return a normal that is 0, 1. Now, that's for the sides. What about the corners? The corners, all we need to do is check to see if any of the corners are met. If they have, it is the same way to calculate the normal. So let's look at that for an example. Our object here, Actually, let's... Yeah, that's fine. And another object here. So we have a side collision here. Here's the position for there. And here's the position for there. If any of the sides are met, we get the delta, the change of positioning. So the delta is here. This is the delta. The change of positioning. So if any of the sides, any corner I should say, any corner is valid, it's the same formula. Normal is equal to the vector change of x, comma, change of y. That vector divided by its length. Change of x, comma, change of y. So that normalizes it. A normal vector is a vector that has a length of 1. To normalize it, you just divide by its length. And that's what we're doing here. On the coding side, it would look like this. Normal is equal to new vector 2 change of x, comma, change of y, and then normal dot normalize. So that is all we need to do for any corner that is valid. But on the side, we need to do the calculations as you see at the top. Alright, so let's recap on how to check these sides. For the right side, here, the object B has to be to the right of object A. Remember, object B is the one that's going to be manipulated. So object A is going to be the one that we're going to look at when we investigate. So if there's going to be vector reflection that's going to happen, it's going to be on object B, not on object A. So object B has to be to the right of object A. And that's what this condition is doing. The delta x is greater than 0. The absolute value of delta y has to be less than a dot height divided by 2. And what that is doing is that's making sure that the object vertically is within the side. It's not at the corner or past the object entirely. Remember, we just did the rectangle collision detection. We know that there's a rectangle collision. So these checks are guaranteed to be a rectangle collision. So we do not need to check to see if it's less than this but greater than this. We know that there's a collision. So this is probably the most tricky one, and this is for all sides as well. Those components of each side, that's the most tricky thing to grasp. And that is to guarantee that the position, the y position, the delta y position is within the side of the object. If it's any greater than this, it's going to be on the corner. And just for an additional check for the right side, if the object B is traveling to the left, which means the x component of velocity is negative. Left side, if object B is to the left of object A, which means the delta position is negative, if the absolute value of delta y is less than the height divided by 2, that's the same thing we just discussed for the right side. And the object is traveling to the right. That means that the x component of object B's velocity is positive. Top, the delta y is less than 0. That means the object B is to the top of object A. Absolute value of delta x is less than the width of A divided by 2. And the y component of B's velocity is positive. That means object B is traveling to the bottom. And then the bottom side. If delta y is greater than 0, object B is to the bottom of object A. If the absolute value of delta x is less than A dot width divided by 2, and the y component of B's velocity is negative. That means object B is traveling to the top. I will provide this image as a download, and then hopefully that will give you a good idea of where to go. Alright, so I hope you enjoyed this video. This is the first video I had to do with my new Wacom tablet and my new setup. So there were a lot of cuts here and there, but I think I got it down pretty well. So stay tuned for the next video.